Hey there, math peeps. This is Mrs. Marshall, and I'm here to teach you about Newton's law of cooling. And this is the equation. Boop, 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 boop. Doo, doo, doo. And we use this equation to calculate the temperature of an object placed inside a surrounding that is cooler than that temperature of that object. So, for example, a soda can is room temperature. You put it inside of a refrigerator that's clearly colder than the room temperature, and we can calculate the temperature of the soda can after a certain amount of time in the fridge. Or say you have a pack of chicken that you've been walking around in Walmart with for about an hour. Well, now you need to get that thing in the refrigerator before it goes bad. So you can put it in the freezer, which is again colder than the temperature of the chicken you've been walking around in Walmart with for an hour, and you can figure out the temperature of the chicken after a certain amount of time. Why would you want to do that is the question. Well, it depends on the situation and the scenario. So we're going to identify what these variables represent, and then we're going to actually go through some real life situations. So what is T? T is your final temperature of the object. So for our two examples, it could be the final temperature after so much time left in the refrigerator for the soda. What would the final temperature be after 30 minutes? Something like that. Your surrounding constant or your constant surrounding temperature is what C represents. And so in this case, it would be not necessarily the room, but the refrigerator. So we call this an ambient / room temperature. Why? Because the word ambient is just a special word for room. But we don't want to use the word room all the time because it's not always a physical room. It could be a refrigerator or a freezer, like the examples I gave you. The initial temp is what T sub 0 represents, and it's of the object again, and it's initial just like all the other variables that we used in class that have a 0 as a subscript. It's our initial temperature in this case. Our K is what we call the cooling constant, and so it's the rate in which your object is cooling. I like to think of cooling starting with a K because cooling with a K represents K. It's just my way of remembering it. If you have something else, please, honey, feel free to share. And then we have T for time. And this is time in minutes. All right. We have all our variables. Now let's get to the scenarios. Example down below. Something's happening at 9 o'clock. All right, let's figure it out. So it says at 9 a.m., a coroner. So this sounds like somebody's about to be dead. Okay, let's see what happened. A coroner arrived at the home of a person who died during the night. Rest in peace to them. Rest in peace. So the temperature of the room was 70 degrees. Good night's sleep. 70 degrees. I like that. But unfortunately, they're asleep forever. But it is assumed that at the time of death, the person had a body temperature of 98.6 degrees. Okay, they were alive before they died. And then at 9:30, 30 minutes after the coroner arrived, which I don't know what they were doing for 30 minutes, but they took the temperature of the body and it was 85.6. And then at 10 a.m., the temperature of the body was 82.7. So yes, indeed, this person is getting colder. So, yeah, I guess they are indeed dead. So now our question is, what time did the person die? So rest in peace to whomever this is, but let's solve this case. What time did they die? So based on the information we have so far, we need to figure out which variable each amount goes with and then plug it in to the equation. So let's start with what is 70. I'm going to skip the first 9 o'clock. We'll go back to it and you'll know why as we go back to it. So our 70 degrees is the room temperature. Well, from above, we know that that is C. And then we have 98.6 degrees, 85.6 degrees, and 82.7 degrees. We need to figure out what T goes with which one, although we technically only have two capital T's. Regular T, which is our final temperature, and T sub 0, which is our starting/initial temperature. The question is, which one goes where, and which one do we use twice? So 98.6, that is definitely our initial temperature. That is the temperature of the person before they died. And 82.7 is the temperature of the person, well, the last temperature taken after the person died. Now the question is, what is 85.6? Is that T or T sub 0? Well, it depends on time now. So the 85.6, because we have that temperature right before we took the last temperature, and we have a time for when we took that temperature, this is going to be an initial temperature as well. The reason why, we know we took that one at 9:30. We took the 82.7 at 10 o'clock. And so we have a 30-minute time frame in which the two temperatures were taken. And that is where we can use it in the equation. So instead of using 98.6, because we have no idea when this person died, so we don't have a time frame to calculate minutes, we can't use 98.6 because then we won't have a time frame for minutes, and we don't know the cooling constant. So we can't use that number yet. That's why we have a part 1 and a part 2. We'll use that number for the second part. For this first part, though, we're going to use 85.6. And our C, again, room temperature is 70. Our T, ending temperature, is 82.7, or final temperature taken. And our K, we don't know. And our T, we do know, is 30 minutes. I left off all of my units of measure, but we know that these are all in degrees and in minutes. So let's plug it in to the equation. So 82.7 equals 70 plus 85.6 minus 70, e to the negative k, well, it's an x because we changed it to an x, well, because we don't know it, times 30. All right, now let's solve this. 82.7 we subtract to try to get x by itself is 12.7 equals, then go ahead and solve that. 85.6 minus 70 is 15.6, e to the negative, and then I'm going to put 30 in front of the x so that our coefficient is in front of the variable as we normally write it. Okay, so now we divide by 15.6 because the goal is to get e, well, the x, not the e, but the x by itself. And we have this, and it's like dag. So what do we do now? Do we divide by e, times by e, subtract? Like, what do we do with e? Oh, wait, do we do something with the negative 30? Wait, what do we do? So you think about what Miss Fisher taught you in her previous video. You take the log or the natural log of both sides. In this case, it would be natural log. However, the way I taught my students was we flip-flop these and we do the love train, yeah, yeah. So let me show you what that looks like / what I mean. We rewrite it. The reason why we rewrite it is because our love train, well, since I kind of just gave it the name, I decided that it's going to go in one direction, and that is to the right. So we start with the E and go right. So I want my single value to be to the right. I don't like to do the love train backwards. It kind of confuses me. I'm like, wait, which one goes where? Where do I put my loop at? So when I write it this way with the single value to the right, I go in the same direction as the love train has always gone, to the right. All right, and then we rewrite it. But we rewrite it in terms of log because we use it to go from base to a log versus log to a base. This doesn't have a log, so we give it one. And it's natural log base E of 12.7 over 15.6, which equals negative 30, x. All right, now remember though, negative 30, oh my gosh, wait a minute. It's right beside the x. And oh, look at there. Both things are not in the exponent anymore. They are on level ground. So yes, honey, get that negative 30 gone from the x, and you are in there like swimwear. Now let's get rid of it. But remember, the natural log, I'm going to go ahead and just take that e off because natural log of e, or natural log base e, is the same thing as just natural log. So I'm going to take that off, make it more simple. and divide by negative 30. And that is what x is. Yes. And now we just need to plug it in our calculator and figure out what that equals. But don't forget your parentheses. So once I plug it into the calculator, I get 0.00686. Well, it's 685 with some stuff behind it, but it rounds to be 686. But I don't want you to use this as your answer. No, don't use this. What you are going to do is you are going to press stow. Some of you may know what stow does. Others may not. I'm going to pretend like nobody knows what it does. So stow. Stow is what you press in order to store a value in for a variable on your calculator. And so you're going to press X, the X button that looks like that. And it is going to store your 0.00685 blah, 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 blah in as X. But you have to make sure you, of course, press enter because it will not activate if you don't press enter. And then you're going to use X for part 2 instead of using the actual numbers 0.000, 686, all that stuff. You're going to use X literally to calculate the next equation from part 2. Instead of like using X on the graphing screen, you're going to actually use it on the computational screen, and it's going to be okay, and it's going to be right, and it's going to be what we're going to do. So let's go ahead and do it. Let's fill in our little values first, of course. So let's start with C. C is 70 again, and our final temperature is 82.7 still. Our initial temperature, now we're using the 98.6 because now we want to figure out the time. And then we have K. K, instead of me rewriting that whole number 0.0 blah, 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 I'm going to write stow because I know that I stored it into the calculator. And then I plug it in again. And so we get 82.7 equals 70 plus 98.6 minus 70, and this is e to the negative. Instead of me writing stow, I'm going to write negative k because I know I stowed it. I just don't want to rewrite sto every time. I'm just going to put k. And then, of course, x because we don't know that. And then solve just like we did the first time. 12.7 equals this time 28.6 when we subtract. And then e to the negative kx. And then divide 12.7 divided by 28.6, which equals e to the negative kx still. And then, do the love train, yeah. So I flip-flop it, boom, boom, and boom. And then do the love train. And I get the natural log. Remember, natural log base e is the same thing as just natural log. 12.7 up, not 15 this time. We are going with the 28.6, which equals e to the negative k. Miss Marshall, what you doing? Which equals negative kx. All right, there we go. And then we want to solve for x. Natural log of 12.7 over 28.6 divided by negative k equals x. But remember, as you plug this into the calculator, remember, use x. And so when you go to press the value for k, do not press stow again. No, don't press 0.0. Don't press all the numbers. Press the button where you get the x from, because we stored that value for x. But you also have to press negative because we didn't store a negative k. We stored a regular old positive k. So you got to make sure you press negative x. And then you get x equals 118.41. And this is time. So our time is in minutes before, because we're trying to calculate what time the person died. So that happened before. But before what time? Well, before the time we took the last temperature. And the time we took the last temperature was at 10 a.m. So it's the minutes, 118 minutes before 10 a.m. So let's figure out what the time is, since that's specifically what they want us to answer. So we have 118, and I'm going to just leave the 41 off. We're going to just round. 118 is the same thing as 1 hour and 58 minutes. And so we take 10 o'clock and we subtract 1 hour and 58 minutes. It's about 2 hours, but it's 2 minutes shy of 2 hours. So that's 8:02 a.m. is the time this person died. Rest in peace. But we solved it. We did it. Yeah, we did it. And you can do it without me. This was a very detailed problem. You had two parts. Yes, you will have to do two parts on your own. Yes, you will. So make sure you study it. Look back over this video in case you need to, for me to, I guess, say what I've already said again, just to hear it again. Hey, this is a video. Rewind it as many times as you like. However, we are going to do some of the Newton law problems where you don't have two parts, you only have one part. So let's scroll on down to example number 2, and we're going to solve this one, which involves just doing Newton's law one time instead of 2 times. All right, so we have Theresa. Theresa was late getting ready for a party. On Theresa. But she had some sodas. At least she, had the drinks ready. But they were at room temperature. And the room temperature was 73 degrees. And the guests were due to arrive in 15 minutes. I don't know if that's enough time to get those drinks cold enough. We'll see. If she puts these in her freezer, she's putting them in the freezer. She should be good. Will the drinks be cold enough at 35 degrees? And our K is 0.031. So let's figure it out. Oh, well, look at there. I have already written it over there on the side. So we have 73 is our initial temperature, which is the beginning temperature of the soft drinks, not the room. And then you have our K, which is 0.031. We have T is 15, and C is -10, and which is the room temperature, which in this case is the freezer, our surrounding temperature. And the temperature we want it to go to is 35. So now, let's not forget what the equation is. T equals C plus T sub 0 minus C e to the negative KT. And now again, let's plug it in to the equation. And so this is 35 equals -10 plus 73 minus -10. So don't forget parentheses. So that is minus a negative. So you got a double negative going on. E to the negative 0.031 times 15. Now, you have everything you need for this one. Literally every single number is filled in. So what you're doing is just verifying. You just want to make sure that that left side 35 is the same thing you get on the right side. So hopefully you're typing it in. I'll give you like 5 seconds. 4, 3, 2, 1. And you get the fact that no, it's not the same. It's 42.135. And so, are they cold enough? Nope, they are not cold enough. Dang on it, Theresa. Gee, you always late. I bet you she always late. But if I was her friend, I would know she always late. And I would come prepared with my own cold drink. Just because you know how y'all friends do. Friends are the way they are forever. So, Theresa, get it together. But no, the drinks aren't cold enough. So hopefully, she could have ice. That could fix it. At the end of the day, this was an example on how to use Newton's law technically once. And in this case, we were just verifying. There are cases in which you do use it once and you're not verifying. You do have one unknown variable. So I want you to try number 3. 3A, 3B, and 3C, honey. Try all 3 of them. What I do want you to make a note of, though, before I, suggest that you pause, is that K is equal to 0.35. It should not be negative. Reason why it's not negative is because in the equation, K has to be a negative in order to cool. So if you're going to plug a negative into a negative spot, it'll then turn positive. So it's not cooling. So it needs to be negative. So that was just a typo. All right. So here's what I want you to do. Pause it. Pause the video and try 3A, 3B, and 3C. If you do not pause, shortly you will see the answers scroll right on up because that is what I'm going to do at this time unless you pause. All right, and here they go. Check your answers. I'm so extra, guys. Not even sorry. I love it. But here you go. There's the work for it. I did a little love train action. I flip flop some stuff around. Just take a look at this work. Hopefully you got what I got without me, because that's always the goal. I tell my kids the goal is to get what I get without me. Hopefully you did. If you didn't, please feel free to rewatch the video. You can also come ask me questions, ask your own teacher questions if you are not one of my students. And for my students, you may come and see me during lunch, specifically tomorrow, which is Friday, October 4th. If you don't come see me tomorrow, Friday, October 4th, then if you come see me next week during lunch, that's fine. I won't turn you away. But I do offer tutoring on Wednesdays from 2:30 to 3:30. All right. Y'all have a wonderful weekend, wonderful week, and I will see you soon. Thank you for being flexible. Marshall is out.